Hello, testing?
Yes.
There we go. Hello, hello. But is mine working? Okay, thanks a lot. Thanks, Paolo and Junaid. Okay.
Feel free to continue the start of your talk, Andrea.
Thanks. So yeah, the aim of this talk is to recall some notions about the Yang-Baxter equation of algebras, quasi-triangle of algebras, and then go into reflection equation and K-matrices. Right, like this. So oh. Now this is not working. So yeah, the mantra of this talk is explained the following picture, which I found from the paper of Lowitz, Walton, and Yakimov. So if you like quantum enveloping algebra, then you should also like quantum symmetric pairs, and it's the same. If you want to do the analog, so universal quantum matrices are the type A analogs of universal quantum K matrices, and so on. So we are going to see a little bit of the quantum reflection equation and braided model categories as well. And so, as I said, let's start with some notion which probably you know very well. So let's start from bialgebra H. This is said to be quasi-triangular if there exists an R matrix, which is an invertible element in H tensor H, satisfying the following axioms. So the first is saying that if you twist if you take the composite co-multiplication, this is exactly the co-multiplication up to conjugating with the R matrix, and then we have the so-called hexagon relations. And if you have a universal R matrix, then it's easy to see that the quantum Yang-Baxter equation is satisfied. You may also know that if you have quasi-triangular bialgebra, there is a way to obtain other quasi-triangular bialgebras, and this is the twisting procedure. So to do this, you need a Drinfeld twist, which is an invertible element again in H tensor H, satisfying the following axioms. And if you have such an element, then you can obtain a new quasi-triangular bialgebra by twisting the co-multiplication and their matrix and taking the same algebra structure. Okay. And now for later use, I think Andrea is gonna use this notion a lot. I need to talk about twist pairs. So take quasi-triangular bialgebra and now take automorphism, an algebra automorphism psi from H to H. Then, of course, you can build another quasi-triangular bialgebra on H, and this is basically by pulling back the structure on H to itself through the map psi. So, in particular, the new co-multiplication is given by this formula, as well as the counit and the R matrix. So note in particular that for the R matrix, we're going to use this notion. So it's R psi psi, in the sense that we're going to apply psi to both legs. And for later use, we are going to use R psi to denote just psi tensor identity applied to R. And if you have a Drinfeld twist, so okay, take a quasi-triangular bialgebra. If you have a Drinfeld twist and automorphism satisfying the following, the following axiom. So if you twist H, this is equal to taking the pulled back structure on H, but with the composite co-multiplication. And if the twisted R matrix is the pulled back R matrix up to a tensor sweep. If this is happening, then we call J psi a twisted pair. Okay. Next, we have braid groups. So you know that, okay, this is, I didn't want to spoil, but next slide we will see. So let's introduce the braid group of type A. So this is as usual generated by n-1 elements, which are the simple braids. For example, you can see sigma 1 is the braid applied to the first two elements. and sigma 2 is the braiding, is the, yeah, the braiding applied to the second and the third strings and so on. And then we have the Yang-Baxter equation, so the usual braid relation. And this is the braid group of type A.
Gives
Yeah.
you a reading from up to down, or
Good question. Okay, I probably in the whole presentation I make a mess between up and down and up, but okay, in this case from up to down. Yeah, thanks. And okay, so later on we're gonna see the type B counterpart of these braid groups. And as usual, if you have a quasi-triangular by algebra H with our matrix R, you have the usual results saying that the category of left modules over H is a braided modal category, and the braiding is given by the action of the R matrix in this way. And in particular, for any n module over H, we can build the representation of the braid group of type A on n strands in the usual way. So you send the generator to the corresponding endomorphism, in which basically you act on the I plus I and I plus 1 elements with their matrix, and then you apply the tensor flip. Okay, now we are going to move to the K matrices. So now fix a quasi-triangular by algebra HR, and recall that the R matrix satisfies the Yang-Baxter equation. Now another element K, now is in H, is called the K matrix if the quantum reflection equation holds, which is the following. So I stole this picture from some Andrea's slides. So these now are going from down to up, and if you represent the action of the R matrix in this way, so the fact that the R matrix gives you a flip, then we can represent the action of the K matrix in the following way. And if this is going to represent the Yang-Baxter equation, we can use this notation to represent the reflection equation. So you can think of something that bounces against a wall. And this, okay, now the question is, now we want to find the solutions for this equation, and this motivates the definition from Andrea and Bart, which is the notion of a cylindrical bialgebra. So cylindrical bialgebra now consists of some data. We have a quasi-triangular bialgebra H with universal matrix R. Then we have a right coideal subalgebra, which means that it's a subalgebra of H satisfying the following, such that the co-multiplication applied to B stays into B tensor H. Then we have a twisted pair. And then we have a K matrix, which in this case is an invertible element satisfying the following two conditions. So if you want to act with the K matrix, this is the same. This is sort of commuting up to the twist, and then the multiplication on K satisfies this condition. And you can see that any cylindrical bialgebra gives you a solution of a generalized version of the reflection equation, which is the following. So if you see the one before was without psi, now we have some psi's involving. And as Andrea told me, the reason is, so if you want to understand why do you need this psi's, is just because if you want to look at examples, then you need to modify a bit to have interesting ones. And I think that Andrea, later on, we will show you some very interesting ones.
there is an R matrix missing in the product identity.
There is an R matrix missing in the coproduct identity, as Andrea says.
There is an R.
Okay, right. So here, an R matrix is missing. Thanks, Andrea. And okay, so cylindrical bialgebras are attached to solutions of generalized reflection equations. And another kind of reflection equation is attached to the so-called reflection by algebras. So similarly to the cylindrical ones, those are made of some data. So we have H by algebra, R and R matrix, then B, psi, and J are as before. So B is a coideal subalgebra, psi and J are a twisted pair. And now we have a bold K matrix, and this is called tensor K matrix, and now is an element of B tensor H and satisfies the following axioms. And if you have such a data, you have a solution of this kind of reflection equation. Okay, and you can go from a cylindrical to a reflection by algebra in the following way. So if you have a reflection by algebra, so we have a tensor R matrix, you can apply the co-unit to the first leg and obtain a K matrix in the sense of a cylindrical by algebra. And also the following formula is satisfied. So the tensor K matrix is you can be is attached is related to the the normal K matrix through this formula. And conversely, if you have a cylindrical by algebra satisfying the same identity that we have here, then you can build a tensor K matrix through this formula. Okay, so why is this the type B counterpart of the R matrices? So let's see this. So first we need to introduce the Artin braid group of type P. So this is again generated by n-1 elements, but we have another extra element called sigma 0. And for type A elements, they satisfy the same relations of braid group of type A. And sigma 0, the new generator, satisfies this reflection equation. So now the pictures are a little bit different because now we are gonna denote by a red string you just not use the red to denote the first string, and you denote sigma 0 in this way. Now it's from bottom to up. And so you take basically the second string and you rotate so first up and then bottom through the red string. And then this reflection equation you add is represented by this picture, which I did a couple of minutes ago, so I hope it's correct.
Yeah.
There is a missing sigma 0 where? In the picture. This?
No, right, like extreme right.
Ah, extreme right. Yeah, exactly. There is a sigma 0 missing. So I did it a couple of. I wanted to use my tablet also for this to modify eventual mistakes, but okay. Yeah. Anyways, this is the relation. And okay, so if you want to understand also why this is the generalization, so everything is the type B counterpart of the type A stuff, I need also to talk a little bit about braided monoidal categories. So those are pairs. So we have a category, a braided monoidal category C, and another category D, together with a functor from D times C into D, satisfying some axioms, and these axioms is essentially are saying that if you think about C as a monoid, monoid category can be thought as a monoid, then D is a module over this monoid C. This is in order to avoid a lot of diagrams. And also, of course, we have a braided monodal category. So you want that this action is braided. So you want a natural isomorphism of this form, labeled by pairs, satisfying again a bunch of axioms, which are the compatibility with the braided structure of C. And this in particular gives you an action of the braid group of type B on this element. So for any M and V, so M in D and V in C, we have an action.
Sorry, for the C and B.
Yeah,
You have M, so B acting on M and also B acting on M on the right. So here there's no flipping because there's no way to act like from the left. Okay. It looks very different to a braiding where you would actually do something like this.
yeah, exactly. No, indeed, this is compatible with the braiding, but yeah, it's not a braiding like stuff. Yeah,
This should correct your S0. So you think about S0,
Exactly.
let's go around because then you go back where you
yeah, exactly. That's why also we represent S0 in this way, no?
that way.
The
Yeah, thanks. And now, okay, let's briefly look at some results and comments. So if you have a reflection by algebra, so remember this is a quasi-triangular matrix, a co-ideal subalgebra, a twist pair and a tensor K matrix, then we have that the pair modulus of H modulus of B is a braided module category. And in particular, you have actions on the braid group of type B, and this action is given in the following way. So you take a module over H and another module over B, and then you can build your representation in the following way. So again, the sigma i's are going to the f i's as in the type A setting, but now you have a sigma 0 going into F0, and F0 acts in the following way. So you have the tensor K matrix acting on W tensor V1. So remember, the tensor K matrix is an element of B tensor H. And okay, in particular here, if you really want an action on the braid group of type B, you need to assume something on the automorphism psi, for example, that V psi is isomorphic to V. So V psi is the pulled back module through psi, acting on H psi. And I think I went very fast, so that's it. So this is a very short bibliography. So if you want some other references, you can ask Andrea because he's much more expert than me. And thanks for your attention and feel free to ask any questions.
Right. Questions for okay. Yes, I have a question on the picture, like where you said
The wrong one.
not the wrong one, but where you introduced one of the first K-matrices where you said that okay, you can think of this as like bouncing from a wall. So yeah, this wasn't fast, so I couldn't really follow. So can you maybe you just say it again? I can see why this is like a particle reflected from a wall.
Okay, so look at the reflection equation, okay? So, okay, look from the right. So here we have an R matrix. So you remember an R matrix represents a twist, sorry, a braiding. So this is giving you this part on the bottom.
So I should now look at the red and the green line.
Yes, yes. Then you have one tensor K here, and then the green part bounds on the let's say the wall, this boundary, yes, Andrea says. And
so the green line hitting the wall here is the times 1 tensor K.
Yeah, because K acts on the right, so like one tensor K is on the green one, the green one is on the right. Then you flip again here, but now you bounce with the red one. So it's K tensor 1. And on the other hand, on the right-hand side, you have this left-hand side.
Okay, this is much better. Okay, thanks. Now I'm
Thanks.
Maybe if I can a second question.
Yeah.
So in the example where you had the co-ideal subalgebras, can you go to this? Yes, probably this one, right? Yes. So I was thinking, so if you just have a quasi-triangular bialgebra, can you somehow set everything else trivial? So if you set K equal to 1, and maybe psi identity J maybe equal to R?
Probably you see it better in this setting, right, Andrea? Because if you can take Okay. Yeah, anyways, yeah, there is a trivial solution.
What I said, so you take K equal 1, psi equal identity, and J equal R, or
And B equal H.
and B,
Yeah.
B equal H.
Exactly.
Okay.
So the point that you look always at the defining equation of the B matrix. So if you choose your B to be the full algebra, then and psi to be the identity, for instance.
Yeah.
So you need to have a central element. And so if your element is central, then you can certainly choose it to be the identity.
Yeah. He's talking to about K.
Yeah, this would work. So here in the delta K, there's something missing. There's an R. So that's why probably you have to choose J equal R.
Yes, okay, if you choose J equal R, then I agree with you.
And the interesting part now, when H is a Drinfeld-Jimbo quantum group, for example.
Those are actually, yes, and then you said yeah, and then Steve was saying J to be R, and then you will see also the co-product with entity groups. That was the central J and R, the missing R.
Yeah, the missing R here. Pardon.
But conversely, you can also choose something like yeah, there are a bunch of choices you can include. Simple examples. Simple object.
Okay, so Paolo had a question in the chat.
Yeah, I can open the probably yes. Okay, thanks, Paolo, for the first comment. And the second, it says, is the Katz-Payutkin of algebra is an example of a cylindrical bialgebra? I don't know. Andrea doesn't. So thanks for the question, Paolo. But I mean, to be honest, I don't know very well this of algebra. I remember, yeah, no, I don't remember. But thanks for the question. Thanks.
So I understand it correctly, like if you go to the Drinfeld-Jimbo, then the B here is going to be your your quantized universal enveloping algebra corresponding to the quantum symmetrics.
Yes, exactly. So the setting is you take Lie algebra, you take an automorphism theta, you take the fixed points of the Lie algebra, and then this is exactly your quantum symmetric pair. So the UQ of G theta is the co-ideal. Yeah.
And what do the other, could you go back, just maybe so I can try to understand the definition in the example.
Here?
Here, I guess, yeah. So the quasi-triangular structure is the usual one. Sub-algebra is UQ.
Yeah, yes, exactly.
What's J?
What is J? That's a good question. You will see in Andrea's talk.
Okay. And maybe a more naive question. So if you got the A series appearing, then you go to modules, you get the B series, what about C and D?
That's I think I asked this question to Andrea also a couple of days ago, and C is like B, and D is there exists the type D equation. I don't know the name, but it's not clear how to interpret this.
So yeah, there are so Nick brought stuff in every type. So that one you can actually do it, and then you can use AK algebras to construct a kind of structure that you are looking for, and almost tautological. And so for instance, there is also a particular type G2 equation that he actually wrote 40 years ago. But I would say for the moment, A and B are the only one that we can understand a little better in off-algebra setting, like in quantum groups and so on. And even type D or this type G not clear what the examples are.
Yeah.
So,
And there's no interpretation like this is A is going to be the.
and it's not even
This is
clear if there is
modular.
a categorical interpretation in that sense. Yeah,
Okay.
I mean, not to me at least.
Okay, thank you.
Thank you.
Yes, so for R matrices or for braided monoidal categories, you can also understand this as a higher category, right? You can like if you have like you can understand braided monoidal categories as two categories, right? So two monoidal categories. Is there something similar you can do for the K matrix to see this as just a higher yeah.
Probably.
Counterpart of the monoidal.
Probably. I don't know. Andrea, I don't know if you want to add something.
No, yeah, I guess you're saying in terms of like understanding I'm just repeating your question. So you just said something like video category as a two category, right? And I guess there should be an interpretation like that in the because there is some work published by David Jordan on some interpretation sense that actually yes, you go in your direction. And then very interesting.
So yeah, I hope that now this picture is a little bit more okay. And now, yeah, we saw. So in the Andrea's talk, I think we're gonna see some quantum enveloping algebras and some quantum symmetric pairs, and then this was the aim of the talk to present this.
Any more questions from online?
We see in the chat. Apparently not.
There are no more questions, and let us thank Andrea again.
Thank you.
We'll be back at 4 with the main seminar.